In this video, we discuss the root test. I will give you a statement of the test. We'll talk about when we use it, and then we'll do a couple of examples. So here's the test. It's actually very similar to the ratio test. It says, do this. Take the limit as n goes to infinity of the nth root of the absolute value of a sub n, where a sub n is the nth term of your series. You're going to get a number, L. Or possibly infinity. If L is greater than 1, then the series a sub n diverges. If L is less than 1, then the series a sub n is absolutely convergent, or we could say it converges absolutely. Or if L is equal to 1, the test is inconclusive. Try another test. And it should be noted that L will always equal 1 for P series. So of course, if you've got a P series, just identify the value of P and use the P series test instead rather than doing this test. You might say, okay, well, when will I ever use this? We always want to use this if a sub n is something to the nth power, so that when you take the nth root of that expression, the nth power and the nth root undo each other, and you are left with a function that's easy to take the limit of as n goes to infinity. So let me write that down for you. I'm just going to write it as b sub n to the nth power, where b sub n is some other sequence. Now, if it doesn't look like this, but it can be rewritten to look like this, then the nth, or then the root test is appropriate. Also note that if there's a 1 in the numerator, let's say you've got like a 1 over b sub n, and b sub n is raised to the n, you could always rewrite that as 1 over b sub n to the n. So if there's a constant in the numerator, well, this test is appropriate as well. Excuse me. You might say, oh, well, what if there's a 2? Well, that will work as well. Actually, we won't be able to rewrite it like this. But notice that if you take the nth root of a number, some constant, I'm going to just use 3 for example, that's the same as the nth root, or that number raised to the 1 over n power. And as n goes to infinity, this will go to 0, and we'll just get 1 every time, as long as that number is not 0. So yeah, if you have a constant in the numerator here and something to the nth power in the denominator, the root test is appropriate there as well. But most of the time, I use this test whenever the nth term looks like this, or it can be rewritten like this. So it is something raised to the nth power. So as soon as I see this one, I'm like, obviously root test, because I've got all of this raised to the nth power. Okay, so I see this problem, that's the plan. I'm going to use the root test here. So we take the limit as n goes to infinity of the nth root of the absolute value of a sub n and here is my series. So this is my nth term. So I'm replacing a sub n with all of this. And notice that this is always positive for n greater than or equal to 1, so the absolute value bars are no longer necessary. Well, the nth root and the nth power undo each other. So we just end up taking the limit as n goes to infinity of this expression down here. Not bad. It's an infinity over infinity indeterminate form, so we're going to do what we always do. Now, if it wasn't a rational function, I might change the n's to x's and use L'Hopital's rule so that it's appropriate to take derivatives. But if I've got a polynomial divided by a polynomial in n, I always use this technique. In order to get rid of the infinity over infinity indeterminate form, we divide the numerator and denominator by the highest power of n in the denominator. So we're going to divide by an n cubed. That's the highest power of n in our denominator this time. So we've got 5 plus, because this divided by n cubed is just 5, 2n over n cubed. Well, one of those n's will reduce and we get 2 over n squared, plus 3 over n cubed is our last term. All that's divided by this. 6n cubed over n cubed is 6. 3n squared over n cubed is 3 over n, and then I have a 1 over n cubed as my last term. As n goes to infinity, now we don't have the infinity over infinity indeterminate form anymore. This goes to 0, this goes to 0, this goes to 0, and this goes to 0 because a number over something very large is going to be very small. And as this gets larger, this gets smaller. So all of these guys go to 0, and we end up with 5 over 6. That's our limit, and that's definitely less than 1. So the series that we started with up 6n cubed. This series is absolutely convergent. It doesn't really mean much because there's no negative terms. It's convergent. By the root test. Now this next example is similar, but you've got to use some exponent properties first. It's almost misleading. You might think you know what this converges, or you might think you immediately know the behavior of this, but you might be wrong, unless you remember your exponent properties. So this does not look like this, but it can be rewritten like that if I use my exponent properties. Now the relevant exponent properties are these. If you've got an x to a power, raised to a power, you have to multiply those exponents. And I can do that backwards too. Like most of the time in algebra class, we went from something that looked like this to something that looked like this. We don't have to go from here to here. We can go from here to here as well. So when I see all of this to the 2n, I'm thinking that's not 2n plus 1 to the 2n, or it is that, but I can rewrite it. I can write that as 2n plus 1 squared to the nth power. You might say, what's going on there with the brackets? It's just another grouping symbol. Don't worry about it. All I'm doing is that. This squared to the n is that to the 2n, according to that rule. So I'm just using that rule backwards. And then over here, I still have the same 3n squared plus 2n plus 4, all raised to the n in the denominator. And then we have this property from algebra as well. If you've got a to the n over b to the n, you could rewrite that as a over b to the n. In algebra class, most of the time we took something like this and we rewrote it this way. And this time we're going this way. So I've got something to the n over something else to the n. So I can write that as one large fraction. In this numerator, that's 2n plus 1 quantity squared. Remember, that's not 4n squared plus 1. Don't square that and square that. You've got to write that twice in FOIL, or write that twice in distribute. Or maybe if you remember that a plus b quantity squared formula from algebra, you could apply that here too. That's appropriate. We have 2n times 2n is 4n squared. Outer times outer is 2n. Inner times inner is another 2n. And last times last is 1. Ah, yes. Now it looks almost identical to the last problem we did. But look how different it is. That 2 made a very big difference in that numerator when I take the nth root. I think it's going to have some consequences for the convergence of this series. So let's compute the nth root of the absolute value of a sub n, and then compute its limit as n goes to infinity. We have the limit as n goes to infinity of this. That's positive all the time, so the absolute value is not necessary. Excuse me. So I'm replacing a sub n with all of that to the n. And remember, the nth root and the nth power undo each other, and we're left with this. And I've got another infinity over infinity indeterminate form with a polynomial over a polynomial. So we divide the numerator and denominator by the highest power of n in the denominator, which is this n squared. And remember why we do that. When we do that, this divided by n squared is just going to give us a 3. Since these other terms involve n to a smaller power than this n squared, like these guys are going to go to 0 when I divide by n squared, and this guy is going to go to 3. So we'll end up with 3 plus a bunch of terms that go to 0. And that's why we do it. It gets rid of the infinity in the denominator for that infinity over infinity indeterminate form. In the numerator, do the same thing. 4n squared divided by n squared is 4. 4n divided by n squared is just 4 over n. One of the n's will reduce, and 1 over n squared is the last term. And as n goes to infinity, this guy goes to 0, and this guy goes to 0, and this guy goes to 0, and that guy goes to 0. I don't know why I like to personify my functions, but I do sometimes. It's 4/3. That's definitely greater than 1, and if our limit is greater than 1, that means our original series diverges. By the root test.